Okay,
Good to go.
so we are super happy today to have Kyle Butts, who is at the Econ Department at University of Colorado Boulder, presenting his paper, Difference and Differences with Spatial Spillovers. Questions welcome throughout. And with that, I'll pass it over to you, Kyle. Thank you.
Great, thanks. Yeah, definitely. If you have questions, just interject. Let me open up the chat real quick too. I'll have that off to the side. But cool, we'll go ahead and get started. I know this group has been reading a lot of papers with differential timing, treatment turns on at different points. And so I'm going to offer you a nice reprise for the first part of this presentation where we're just going to be thinking about like a 2x2 case. So that should be nice. But in particular, I'm going to be thinking about how to accurately estimate difference in difference in the presence of this thing called spatial spillovers, which I'll sort of define for you. So researchers typically, the goal is trying to find this tau, which is the average treatment effect on the treated. But estimation is going to be complicated or harder to achieve whenever we have spillover effects. And so you can think of this as when the effect of treatment, right? We like say treatment is defined by some administrative boundary like a county. It's when the effects of the treatment extends over the treatment boundaries of assignment. So let's use an example of Amazon Shipping Center. If a shipping center opens in a county, it has potential to have positive employment effects on nearby control counties. If it raises average incomes and that spending doesn't just occur in the control or the treated county and it goes over to other counties, there's going to be potential employment effects on those counties as well. And then there's also like having nearby counties that are that also have shipping centers can raise employment in the commuting zone and therefore can reduce the effect of the treated county. So the treatment effect might actually depend on the treatment status of your neighbors. And so in this paper, what I'm going to do is I'm going to introduce a potential outcomes framework that like formalizes what a spillover effect is. And it's going to also, I'm going to use this framework to evaluate what's currently being done to try to control for these things in the literature, and then offer some alternative solutions that I think are superior. I'm going to propose an estimation strategy that improves, and it's going to be more robust to both forms of spillovers I discussed, both spillovers on the control units and also spillover effects on other treated units. And then in the paper, I apply this framework to look at local effects or estimates of local effects of place-based policies in urban economics. And we'll get to those examples in a moment. So thinking about, this is sort of a preview of my result, my central result, the canonical difference and differences estimator, the 2x2 case, the easy one. We have our estimate for the treatment effect is the change in outcomes among treated individuals. So this is period 1 minus the initial period among the treated. And that is supposed to be an estimate of the counterfactual trend that's supposed to be constant between treated and untreated groups, plus the treatment effect. And then we have the change in outcomes among the untreated units. And that's just supposed to be our estimate of the counterfactual trend. You take the difference of these two things and you end up with tau, ideally. But I'm going to show you that there's two problems that occur in the presence of spillover effects. First, when you have spillover effects on the control units. So nearby control units, they no longer are going to estimate the counterfactual trends because they're actually affected by treatment. So this second difference, the change in outcomes among the control units, it's going to pick up on that counterfactual trend that would exist in the complete absence of treatment. As well, it's going to pick up on this spillover effects that if the control counties have positive employment gains because of the Amazon shipping center in nearby treated counties, this change in outcomes is going to be estimated too large. And when you subtract away that second difference, the spillover effects is going to be subtracted from our estimate of tau. So that's going to be the first source of bias. The second bias is spillover effects on other treated units. So treated units can be affected by nearby units, and therefore you're going to get an estimate of tau plus the spillover effects on the treated units. So that's the second source of bias. And because this is the first difference, the spillover on treated effects is going to bias the same magnitude of the spillover effects. And because you subtract away the change in outcomes in the control unit, if you have spillovers on control, the bias will be the opposite sign of the spillover effects. So if you have a positive spillover effect on the control counties, that's going to be a negative bias on your coefficient. And likewise, if you have a positive effect on other treated units, that's going to be a positive bias on your tau estimate. And so that's the first result, is this decomposition. It just uses basic potential outcomes. You add and subtract a bunch of terms, and you get that when you estimate this difference in difference, you're actually just going to get tau plus the spillover on the treated minus the spillover on the control. The second thing I'm going to show you, so this is the first result, is that when you estimate a two-way fixed effect model without differential timing, so this is the 2x2 case, the expected your estimator, the expected value is going to be just the true treatment effect. Oh my God. Terrible, sorry. This is a minus. It is, you subtract away the average spillover on the control units, and then you add the average spillover on the treated units. And so you're no longer estimating the treatment effect. You're estimating a combination of three effects. And so the solution, because when I get this is going to be the average spillover on control units, and this is going to be the average spillover on treated effects. And we actually have a really easy way to estimate averages, and that's just using an indicator variable. So if you modify the regression to have this within dummy variable, within will be equal to 1 if you're within a certain distance from the treated unit, and it will be equal to 0 if you're further away. And likewise, if you interact that with treatment status in that period, you will remove both sources of you will remove both average spillover effects, and therefore you will be left with an unbiased estimate of the treatment effect. And that is true so long as within contains all the units that are affected by spillovers. So effectively, if you have a map of let's say this is the US, I'll do my best, I'll paint Florida and so forth. And you have one treatment, just simply one treatment, and you say, okay, this is within, and you have an indicator for being any of these counties within this area, and you estimate it, you will use all the other counties, all the outside counties, to estimate the counterfactual trend, and these inner counties will estimate the spillover effect and remove it from your estimate. And so you end up with an unbiased estimate. So that's the second result. Is a lot of papers, they try to parameterize how the spillover affects carryover distance, and you will remove all the bias so long as you accurately parameterize the spillover function, which is something that, as an applied researcher, we don't know what that actually looks like. And so if all you care about is estimating the treatment effect itself, you don't have to actually parameterize how spillovers travel over space. Instead, you just use a 0-1 indicator and you'll have an unbiased estimate. So thinking about this is sort of a visual example. So on the y-axis, you have the change in y. So this is post minus pre averages, or this is period 1 minus period 0. And on the x-axis, I have the distance from the nearest treated unit. As 0, you are treated, and you can see your average change in outcome is around 4. And then you can see that there's some sort of spillover effect occurring in this region. And then for whatever reason, that 40 miles, that's about as far as spillovers go. And then after that, you're just back to the counterfactual. You're just on the counterfactual trend of 2. So all that the method is, this within indicator just says, okay, if you're between 0 and in this case, 60, I'm just going to give you a 1. And if you're greater than 60 miles away from treated, you get a value of 0 for this within indicator. And so then I'm going to estimate the regression. I'll get a counterfactual trend estimate using these units of a value of 2. And then I'm going to get this within is going to absorb all of these spillover effects that normally would bias my result. And then I would get a point estimate of 4 for the treated. And so I would accurately estimate that the treatment effect is size 2. However, this approach sort of is lacking. The immediate thing you think is, well, I'm not really doing a great job actually estimating the spillover effects themselves. And if I care about the spillover effects, right? If you see being really close to treatment, you have a spillover effect of 3.5, well, 1.5, because it's minus 2. And then over here, you have a spillover effect of 0.5. And then after 40 miles, you actually have a spillover effect of 0. And so the next thing I do is propose to use a set of concentric rings, and this is sort of already done in the literature, like this, where you have a bunch of distance bins. So this is 0 to 15, 15 to 30, 30 to 45, and 45 to 60. And as you can see, sort of intuitively, you're better able to capture how spillover effects change over distance, right? So for being between 0 and 15, you're going to have a larger spillover effect estimate than if you're from 15 to 30, and if you're from 30 to 45. And then you accurately will estimate that between 45 and 60 miles, you actually don't have any spillover effect at all. And the advantage of using these rings, again, instead of parameterizing, is these rings will be collinear with just the original indicator, right? In other words, these 0, 1 variables will add up to just the 0 to 60, and therefore we still maintain the property that our treatment effect estimate is going to be unbiased. And so rings give us like two advantages. Having a bunch of rings lets us both have an unbiased estimate of the treatment effect, and then it also lets us better estimate the spillover effects themselves. Taylor, do you have a question?
Oh yeah, Kyle, I was just going to ask, here our estimate, I think you said it, but I just want to clarify and make it explicit. When we're talking about this bias here, we're talking about as if our estimate is only the direct effect. And so if we were interested in the net effect, then we wouldn't necessarily consider this bias. Is that?
So yeah, if you, for example, if you wanted to know, okay, I'm like a state and I'm thinking about implementing a policy in a particular county, and I want to know like what happens to the state. Then you both care about the treatment effect and you also care about the spillover effect, right?
Yeah.
But your regression wouldn't look like this, because DIT is like just the treated county.
Yeah.
Because then you wouldn't be considering. So you could like have a dummy variable that's treated county plus the neighboring counties as one big thing, and then you can get the net effect. But I think it's better to estimate each effect separately, so you just get a better idea of what's happening, rather than just getting one number, right?
Yeah.
And by the way,
I just wanted to make it explicit that we're just talking about the direct effect and
the direct effect
and everything.
Just among the actual treated units.
Yeah.
And if you had no ring whatsoever, you would compare the change in outcome, which is 4 among the treated units, and then the average change among all the control units would be something like this, right? Because there's a positive spillover effect. And so you'd be estimating a treatment effect that's too small. You'd be negatively biased.
Right.
So the ring removes the bias, but multiple rings just lets you better estimate while still removing the bias. So there's that twofold advantage.
Awesome. Thanks.
Yeah.
Kyle, I have two questions, if I may.
Sure.
So one is, do you imagine that there is a treatment happens in just one point in space, so that the distance from near, or is it like really distance from nearest treated?
Yeah,
in which case,
okay,
so in which case, what happens if your rings overlap?
So it depends on the context, and we'll get to it. If it matters the number of units that are near you that are treated, if the spillover effects are additive in the number of units nearby, estimating.
Right, but at this point you start imposing assumptions on the structure of treatment effects. I thought your point was that you don't impose assumptions.
Yeah, so the unbiased result doesn't depend on, it just depends on that if you capture every unit that is affected by spillovers, regardless of the magnitude, and then you still have extra units that are unaffected by treatment.
Mm-hmm. So even if there is some interaction of like how, okay.
Even if 2 doubles the effect size, being near 2
or not, you don't need to know.
Yeah, you don't need to know. Yeah, exactly. But it does matter if you want to estimate the spillover effects. We'll talk about it. You can either have an indicator set of rings like this, or you can do the number of treated units in each ring if you think that the spillover effect is additive.
Yeah, and then the questions about the literature connection, are you going to tell us a little bit about that, or should I ask now, or should I wait?
In here, how it's connected to the like an econometric literature?
On spatial spillovers, which is substantial.
Yeah, so there's a lot of papers that like use this weighting matrix W, like you like take you would run the regression YIT equals mu I plus mu T plus DIT times tau plus like a weighted, and this is like your spatial weights. And mine's related to it, but I start from a potential outcome framework.
Yeah, but there are literatures which do that and do things non-parametrically, right, in terms of spillovers. So I'm thinking of Michael Polman's paper, if you've seen that, on spatial interference, but also more broadly papers about network interference in this spirit of like local non-parametric spillovers.
Yeah, so those papers, there's like this idea of partial.
Exactly.
They use. It's under the assumption that there's treated groups and spillovers occur within this network, and then there's separate networks, separate from so for example, industries, there could be spillover effects within industries, but not across industries. Is that what you're talking about or no?
I don't know that literature too well, but that was not my sense. I mean, I was thinking of papers like, there was this Hutchinson Cholera and all of those follow-up papers. Frederick Xavier has a number of papers. I don't know if you've seen, which I think aren't on one big network, but yes, they assume that spillovers are local, but that seems to be what you assume as well, right?
Yeah.
With these rings.
Yeah, I'm not sure I know could you send me the name of the paper?
Yeah, for sure. But also Michael Polman's paper seems who also talks about rings of different sizes, but does something different with them from what I see you do. Yeah.
Okay, I'll look into it. Thank you. No, yeah, I'm not sure. So like I said, just an outline, I'm going to formalize I'm going to actually show you the potential outcome framework. So that was sort of an overview, and now kind of getting into the actual theory. And then I'm going to just show you some examples of how to actually apply these, or how these, the improved estimators actually change outcomes in real examples. So just for exposition, I'm going to refer to these units as counties, but there's no reason they have to be counties. It can be any sort of geographic administrative boundary, so to say. And so I'm going to use the typical potential outcome framework, which is outcome for unit I at time t. It depends on treatment status. And if this wasn't here, you would folks should know potential outcomes. And then I'm going to introduce this next thing, which I'm going to call the exposure mapping. And what this is it takes the entire vector of treatment assignments, 0, 1 variable for each all n units, and it summarizes this into either a scalar or a vector. And so this exposure tells you how near or how affected by nearby treatment you are. And in particular, we're going to just normalize and we're going to say that no exposure is the 0 scalar or the 0 vector. And because this is kind of like hard to think about, I'm going to just give you some examples of exposure mappings. So the first of all, there's an exposure mapping that is just being within X miles of a treatment. And that's just the max of an indicator variable for being within X miles. This distance is the distance between your county I and the other county J. And so an example of this, where this is actually a pretty good approximation to the exposure, is, for example, library access, where X could be the maximum distance that you'd be willing to drive to get to a library. And importantly, this doesn't really matter how many libraries are nearby, right? It just matters which one's the closest. In other words, the spillovers are non-additive in the number of nearby treated units there are. And then you could so for a visual example, this is these counties with black outlines. Those are treated counties. And you can see, if you sort of were to draw rings around, let's say rings of size 40 miles around, all the counties that are within that would be affected. They would have access to the libraries, right? But outside of 40 miles, that's just too far to drive to get books, and therefore they have 0 exposure. As a second example, you can think about the number of treated units within X miles. And so now, instead of it being whether or not there's any within 40 miles, you could say how many counties within 40 miles are treated. And so that's the sum of these. And that sort of would reflect if there's some sort of additive spillovers. So in the example of the Amazon shipping center, it actually kind of matters how many nearby counties are treated to determine your exposure. And so therefore, this is like due to agglomeration economies, there's benefits for there being a lot of businesses nearby. And so this exposure mapping might better represent additive spillovers. And so this, you can see that in places with high densities of treatment, you can see the spillovers get larger in magnitude. And so this sort of measures, in some sense, additive spillovers, right? So that's some examples. So now I'm going to just formalize in this new potential outcome framework what the actual estimand we're trying to estimate is. This direct, what do I mean when I say the direct effect of treatment, or the average direct effect of treatment on the treated, right? And so this looks at the expected, in the post period, the expected change in outcome from being treated versus not being treated. And that's in the world where you're not experiencing any spillovers. So if you were the only county that's treated, what would your treatment effect be? This is the direct effect. And then the spillover effects I'm going to define similarly. This first term, the average spillover effect on the treated, looks at in the post period, the change in outcome for being exposed at the exposure level you are, HI, minus the being unexposed. So this is just the effect that being exposed while being treated in both states of the world. So being exposed at HI versus not being exposed at all while being treated. So this is the average spillover effect on treated. And then the average spillover effect on controlled is in the world where you're not treated, the difference in the post period for being exposed at HI versus not being exposed at all. And so if you were to you could write out these, you could write out Y, I1, 1, HI, D bar. This is your observed outcome, right? You can see how this is a composition of these two things. If you were to add this, you can decompose this as Y1 HI. That's not right. Right. So you could add and subtract a term, and you can end up. You can see how the direct effect and the spillover effect on the treated are sort of similar in that the total effect on the treated is the sum of these two. Right. Cool. Any questions on that before I continue?
Yeah, I have a couple.
Yeah.
So first, you previously said that the ring has to be wide enough to cover everybody who is potentially affected, but doesn't need to actually be precisely drawn. So how is this consistent with the formulation you just gave us, where the potential outcome just depends on the scalar, if I understand correctly, exposure mapping?
Yeah, so this is, so the potential outcome, actually your level of exposure can change the spillover effect.
Yeah.
And so, but then in order to just estimate the direct effect, you don't need to estimate accurately for each individual their spillover effect. You only need to accurately estimate the average spillover effect. And so an indicator can estimate that. Does that make sense or no?
I'm not following. So I mean, maybe I'm getting ahead of myself, but does it have to be that you observe HI?
No.
Okay.
Yeah, this is just the true potential outcome. But you don't need knowledge of it. You just need to know. The only knowledge you need to know is how far the spillovers can spread. But
Okay.
I'll formalize that assumption.
Yeah. And the other question I have, when you write these expectations, they seem to assume some IIDness. Otherwise, they would have eyes on them. So what kind of sampling is this?
Oh, just IID. Well, like panel random sampling.
No, but then what is the arrow? Is it on the sampled units, or how should I think about that?
Yeah, no, this is the vector. Yeah, so this is a random variable. It's the vector of treatment assignments. I'm not sure I understand.
Of which units? Of the sampled units or of all potential units?
Yeah, this is like inference under like a superpopulation. Like you're observing, let's say, the U.S. counties.
Yeah.
I'm not sure I understand your question.
Fine, but if so, then yeah. So I don't follow the kind of joint distribution of different i's. If there is just a sample, then d bar is not enough, right? Because you need to know what happened, whether the treatment happened even to the units you didn't sample. And so I'm trying to understand how you avoid this problem.
So I like the context I'm thinking of is like if you have, for example, like a lot of regressions run on the panel of U.S. counties over time, and you have treated
Of all U.S. counties.
Yeah.
Then there is no sampling, no IIDness. That's, for example, like how my paper with Peter Hull works.
Yeah.
But then there is I, and this expectation is I specific.
Yeah. Okay. Yeah. Okay.
But for you, it's not.
You meaning this right here?
Yeah. Well, I mean the left-hand side also, right? If the right-hand side is I specific.
Yeah. Right.
Yeah.
Yeah. So this is average over all treated units. I'm not sure.
So is this an expectation or is this an average? I mean, these are different things, right? Either you have a finite population and then you need to take averages across treated units quite literally among the finite sample, or there is some sampling or whatever that lets you write this expectation.
Yeah.
Those are like different for different frameworks.
Yeah, it's a good point. Yeah. So I mean, I think this is like in a. I don't think I have a good answer for you at the moment, but I'll think about it. I'll just give you some. Thanks. I'll think about it. And so then in a difference framework, we need some sort of potential outcome, parallel counterfactual trends assumption, of course. And so in this case, I'm going to be looking at, we're just going to modify the typical parallel counterfactual trends assumption such that in the complete absence of treatment, so where no one is treated whatsoever, potential outcomes would change the same among treated and untreated units in the complete absence of treatment. So not only are the particular treated units untreated, also there's no other units treated. So I think this is not that big of a change of assumption. It's just a modification to sort of account for the fact that we're thinking in the complete absence of treatment because my potential outcome depends on my exposure as well as my own treatment status. And so with that, using that potential, the parallel counterfactual trend assumption, I'm going to decompose the difference in differences estimate as follows. So this is the standard. The expectation is just the average change in outcomes among the treated units minus the average change in outcomes among the untreated units. And then I can decompose that just by adding and subtracting terms is to the direct effect plus the average spillover effect onto treated units minus the average spillover effect onto control units. And that just comes from adding and subtracting a bunch of terms, and just like the standard proof of difference in differences is unbiased, it just adds a bunch of terms. And so then I derive this. Any questions on that before I continue? Cool. And like I said before, because the spillover effects on controls are subtracted away, the bias is the opposite sign of the spillovers on controls. So if there's a positive spillover effect on the control units, then you would be negatively biased. And if there was a negative spillover effect on the control units, you'd be positively biased. Now, spillover effects onto other treated units, that would be the same sign as the sign of the spillover effect. So then thinking about how to remove this bias, right? We don't want to leave bias in our estimates. If you let dij be the distance between two units, I and j, if you're going to assume that there's some distance d bar such that for all units, such that the closest treated unit is further away than d bar, then exposure mapping is 0. That just says that if you're further away from the nearest treated unit than d bar, then you're not going to be affected by treatment. And then you also need there to be units that are farther away than d bar. So right? If every unit, if every control unit was affected by the treatment, then you would have no control units in effect. So these two assumptions, I refer to it as spillovers being local in nature, that there's some distance that once you get past that, you're not affected by treatment, and that there's some units that you can observe that are past that distance as well. And then with that, if you define, oh, I'm sorry, this should be a subscript T. If you defined SIT, similar to DIT, to be an indicator equal to 1 in the post periods for all units with H exposure not equal to 0, and this can also include some units that are experience no exposure, then estimating the standard two-way fixed effects plus interacting the SIT with treatment status, this tau hat is going to be consistent for the tau direct, the direct effect of treatment. You're going to remove both sources of bias. And the reason for that is because these two terms are average spillover effects on the treated and average spillover effects onto control units. And so if you use these, this estimates the average spillover effect onto treated units, and this estimates or controls for the average spillover effect on the control units. But because you, these spillover effect estimates themselves are not going to be consistent for the average spillover effects themselves. And that's because you're going to have some units, right? If this is my definition of the average spillover effect is among all control units, you're not going to be getting an average among that because your SIT does not include SIT times 1 minus DIT does not include every control unit. So you're not accurately estimating the tau spillovers, but you do have a consistent and unbiased estimate for the direct effect. As an aside, what's commonly done in the literature is instead of directly controlling within the regression, researchers will typically drop from their sample neighboring or nearby control units. And there's actually two reasons I think that this is not the preferred method. First is just removing the control units from the sample is going to decrease the precision of your estimate. You're just lowering the number of observations you have, and therefore lowering the precision needlessly. Adding one extra covariate and keeping a bunch of observations is going to, you're not going to lose as much precision from adding just one covariate. And then also the second reason is that spillover effects on treated units will still remain in the estimate. And so you're not removing both sources of bias when you do this. You're only removing the average spillover effect on control units. Any questions before I continue? That's the end of my theory section.
Do you think, like, which of the results would continue to hold with some heterogeneity of the main treatment effects? I could see that, you start with a two-way fixed effect regression, which has issues to begin with, and by having more right-hand side variables, this can only get worse. For example, compared to dropping some of the neighboring units, which may be better in that way.
That's a really good question. There could be a problem if the heterogeneous spillover effects are correlated with treatment location. So you would have, let's say, you would be how to say this? The treatment effect would be larger for treated units that are near other treated units. Then perhaps including this might absorb that. That's a really good question. I'll have to think about that more.
Take a look at this new work of Peter Holland, Paul Goldsmith-Pinkham, and Mikhail Kolesar about how just having several treatment variables messes things up. I think that might apply to you as well.
Yeah, thank you. So continuing, I have a set of Monte Carlo simulations to sort of emphasize this result or illustrate this result. So I just generate data using with just spillovers on the control units. Details are in the paper, but basically I have some normally distributed time fixed effects that are on a linear time trend that grow over time. And I have unit fixed effects. I have a true treatment effect of 2. I assign treatment randomly to US counties. And then I generate this data with a bunch of different exposure mappings. And we'll talk about which exposure mappings I use. One second. My laptop is dying. Sorry about that. And then I'm going to estimate each data generating process using other exposure mappings, including the rings and the within indicator, and then some other exposure mappings as well. And I'm going to report the average bias that results. So just as before, we have the within indicator and within additive. So the within looks like this. This is for 80 miles. So a ring around each treated unit. Then there's the additive version where in places of high treatment density, the magnitude of the exposure mapping gets larger. It's the number of units within 80 miles. Then what's commonly used in the literature is this decay parameter. So I'll just show you what it looks like. And the exposure is larger for units that are really close to the treated units than a little bit further away. So you can see like, what's a good example? Right here, near rings, they have a larger exposure mapping value than a bit further away. You can see it gets lighter gray. And then there's the additive version too, where being close to many treated units will give you a very large, so you can, large exposure. For example, right here, you can see it's really dark because you're really close to a lot of treated units. But the point of this is I'm just trying to show you under a wide under a wide class of exposure mappings, we're going to see this within indicator is going to work really well. And then I'm going to use also I'm going to use these rings, which are the set of concentric rings. And the additive version of this would just be the number of treated units that belong to each distance bin. And so as an example, there's different exposures. Instead of it just being a single number, it's a set of indicators, one for being between 0 and 20 miles, 20 and 30, 30 to 40, 40 to 60, 60 to 80. And so you can see sort of, if there were to be a decay, if the true exposure mapping were to be a decay, you can actually approximate this really well with rings. In fact, as the number of rings get larger and larger, you would actually be able to non-parametrically estimate any exposure mapping at all. So as results on the each column is going to be a different true data generating process. The withins and the decays, both the non-additive and the additive versions. And each row is going to be the specification. So for example, I'm running the regression using the within 40 indicator. And if I was looking at this column, this would be the true exposure mapping that I'm generating. And I keep the average spillover effect constant. In other words, the two-way fixed effects where I don't control for spillovers, they're going to have the same bias. And so you should be thinking of this as bias relative to the two-way fixed effects bias, which is about 0.258 in this set of simulations. And we can see, first of all, for the within 40 miles, it removes almost all the bias besides some sampling bias. So long as only for those exposure mappings that only go 40 miles. If they go 80 miles, these four, we see that a lot of bias remains. Now for within 80 miles, because it's wide enough to capture each of the data generating processes, we see there's virtually no bias as well. Now, if you go ahead and were to try to accurately parameterize the exposure mapping, if you get it right, for example, here, if you get it right, you will remove bias. But if you get it wrong, for example, decay 80 miles and you say within 40 additive, you're going to have a large amount of bias still. And so the point of this, like one of the points of this paper is you don't actually don't have to try to estimate accurately the exposure mapping if you want to just get a good estimate of the direct effect. You just need these withins. And then also the same thing is true of rings. Because the rings add up to the within indicator, you still are going to have this bias removal property that we like. You see right there. So an indicator or a set of indicators, so long as they capture all the affected units, that will remove all bias. And this is just sort of illustrative. And now I ask the question, What if you actually care about the spillover effects themselves? You don't just want an unbiased estimate of the direct effect. For example, if you're a state and you care about all the counties, not just the treated counties, you probably care about the spillover effect on the control units, right? Do the benefits of the treated counties come at the cost of neighboring counties, for example? Are you just moving economic activity around when you invest in a place, or are you generating new activity? And then you might also care about the spillover effect on the treated units. For example, if I'm a particular county and I'm thinking about implementing a policy, I want to know both the direct effect, and then I also want to know how the direct effect changes based on the number of nearby units that are treated, right? And so to estimate those spillover effects, we want to try to parameterize this H function a little bit better. So what I'm doing is I'm running the same set of simulations, and now I get an estimate for the spillover effects coefficients, right? I estimate the spillover effect for each control unit. So I just plug in the exposure mapping that I'm using, potentially wrongly specified, times the point estimate. And then I'm just going to do a big thing, but the number is it's the mean squared prediction error. So how close do I get at accurately estimating that particular county's spillover effect? And then I normalize and I do 1 minus that, just so the number I get is the proportion of spillovers that I am able to explain for a given exposure mapping. So this number, if it's closer to 100, if it's 100%, that means for every county, I know exactly the spillover effect. If it's 0%, it means I estimate it not at all. And so just again, as a reminder, the single ring does a good job of removing bias, but it doesn't actually do a good job estimating the spillover effects. Whereas the ring is going to do the set of rings is going to do a much better job. And we see that in this results as well, that within, if you get it right, does a good job of estimating it, but it actually doesn't do that good of a job, somewhere between 30 and 80%, depending on the data generating process. Again, for these where you're like doing a lot of parameterization, you don't do that good of a job unless you get it right? So within 40 additive, you can get 99%. But the rings themselves, right? For example, these two rings, they do a really good job. We see quite consistently for these rings, as long as it's not additive, I'm able to accurately estimate the spillover effects themselves. And if the true data generating process is additive in the number of nearby treated units, the additive version of rings is able to accurately estimate those spillover effects. And so donuts, or these rings, they do the best at estimating spillover effects among all of the specifications I looked at, but it's important to get additive versus non-additive correct if you want to accurately estimate the spillover effects. And so what I suggest in the paper is that if you want to get an unbiased estimate for the direct effect, but you suspect that the spillover effects are additive, you might want to run two separate regressions. One, just using a within indicator to accurately estimate the direct effect, and then a separate regression that uses the additive version of the rings to accurately estimate the spillover effects. So now let's actually think about this in the context. Does this matter? Does it have sizable impacts and so forth? So first I'm going to look at the Tennessee Valley Authority, Klein and Moretti. They have a QJE article that looks at the long run impacts of the Tennessee Valley Authority, which the TVA was a large scale federal investment. It started during the New Deal in the 30s, and it built a bunch of dams to bring cheap electricity to the Tennessee Valley to try to stimulate the manufacturing economy. And this actually turned out to be about hundreds of dollars spent annually per person. And the program focused on large-scale dam construction and brought cheap wholesale electricity. So you would think that this would bring in manufacturing and potentially displace farm workers. So they asked the questions like, what are the local effects of the TVA on manufacturing and agricultural economies? And then an additional question you can now ask using my framework is, do these effects come at the cost of other counties? They use a big structural model to ask this question, and I'm suggesting a regression framework to answer the same question. So what they actually do is they do they run the county level difference and different. They use a first differences specification, but when you only have 2 years, that's equivalent. So they look at change in outcomes between 2000 and 1940 for counties. And they have a dummy variable, a treatment variable for whether or not you're in the Tennessee Valley Authority. And then they use a bunch of pre-treatment fixed long-term covariates that will allow there to be long-term trends based on these covariates. Because you're in the first difference, including these allows for differential trends based on these covariates. And then, not to get too into details, they trim the sample using a logistic regression to predict treatment using these same covariates, and they keep the top 75% of predicted probability. They hope that this will improve their counterfactual trends assumption. So thinking about spillovers in the TVA context, there's reasons to believe that spillovers can occur to nearby counties. So for agriculture, perhaps farm workers just outside the Tennessee Valley might be drawn to higher wages from new manufacturing jobs in the Tennessee Valley. So you would have a decline in farm worker employment in the control counties, so a negative spillover. This would bias your estimate of the agricultural impacts upwards. And for manufacturing, there's potentially positive and there's potentially negative spillover effects. The cheap electricity that got brought to the region might have a positive spillover effect on the control units if they also have access to this cheap electricity. However, there could be negative spillover effects if manufacturing jobs that would have been created in the control units in the absence of treatment, they might decide to move to the Tennessee Valley next to other manufacturing businesses. So you'd have a negative shock to manufacturing employment on the control units. And so I run the same regression, the first difference, with the TVA, oh, that should be C, sorry about that, and then a set of rings, just as between 0 and 50 miles, 50 to 100, 100 to 150, and 150 to 200 miles. And so visually what that looks like is this is their effective sample, it's all of the counties that are outlined. And then I just use a set of rings around the Tennessee Valley. 0 to 50, 50 to 100, 150 to 200, right? And so my results look like this. The original estimate is a decline in agricultural employment of 5% in the Tennessee Valley. But because I'm able to accurately estimate that there is a negative spillover effect on nearby counties, the agricultural employment went down around the Tennessee Valley. They were actually positively biased, and the effect is actually something like 7.4%. This is per decade growth, and so this is quite a large difference over 6 decades. It's compounding, right? And 2.3% is quite big as well. And then for manufacturing, we see the same story. They estimate growth of 5.6% per decade, but because there's negative spillovers, it turns out that negative effect dominates across the board. They were positively biased and they were overestimating the true effect of the Tennessee Valley on manufacturing employment growth. Mine's something closer to 3.5%. So these are quite sizable differences. And it has to do with the fact that you're comparing growth rates between the Tennessee Valley and other units that are affected by the Tennessee Valley. It was hundreds of dollars spent per person. And so using these as control units is not so good an idea without directly controlling for these spillover effects. And more broadly, we see this all the time in urban economics. They use this sort of just on the other side of the border versus being within the treated area. We see that a lot in urban economics. So a particular example is there's a giant literature on federal enterprise zones, which are a place-based policy. They're focused on high poverty areas. They are tax breaks that are given to businesses that choose to locate within these boundaries. Some papers find positive effects on poverty rate. Poverty rates decline. Other papers find almost zero effect. For example, there's sort of an overview in Newmark and Young. So Busso and Gregory and Klein, they compare census tracts that are within these empowerment zones to census tracts that were qualified to become an empowerment zone, but were rejected. And these are typically further away. They're like in different cities or different ends of the city. And they find large and significant reductions in poverty. As opposed to Newmark and Kolko, they look at census tracts just within the empowerment zones to census tracts within 1,000 feet of the zone. And they find near zero effects. Now, I can't replicate these because they use administrative data. Wouldn't that be nice to have? But my framework, you can actually explain both of these results if you make the assumption if census tracts just outside the empowerment zone also benefit from the policy, then the estimates of Newmark and Kolko are going to be attenuated towards zero. There's positive reductions, but those reductions are also felt just outside the empowerment zone because businesses are moving in and maybe the workers live outside the empowerment zone or they spend money just outside. Then you're going to just be biased towards zero. And so you can actually think both of these results are true if you make the assumption that just on the other side of the empowerment zone, census tracts also face a reduction in poverty. And so my paper sort of provides a warning to people that are using this identification strategy of just within and just outside the border of some sort of treatment assignment, to make sure to be able to justify justify that there's no spillover effects occurring. Because if there are, you're going to have a biased estimate. My voice is going, so I think I'm going to skip this section. It's a couple slides, but I'm working on a new draft of my paper, and so I think it's not all the way there. So I'd rather just conclude. That's fine. So in conclusion, I decomposed the two-way fixed effect estimate into the direct effect in the two spillover terms. I show that either a single indicator or a set of concentric rings allows for unbiased estimation of the direct effect of treatment, and the concentric rings are able to accurately model the spillovers as well. And so these rings are pretty versatile, and that's what my paper recommends. And then I show for place-based policies, I show that it's important to consider spatial spillovers when estimating the treatment effects. And more generally, I show that identification strategies that use very close control units the goal of this is try to minimize the difference in unobservables by using just on their side of the border. That this identification strategy, it's really important to consider the problem when you have treatment effect spillovers. That's what I have. Do I have any questions? Discussion?
Thanks, Kyle. I was wondering if, I think you mentioned in the paper, but I want to ask as well. How do you, when you're deciding on the width of these bins or these circles, you mentioned there's this trade-off, this bias variance trade-off that you're doing. Is there a way to like optimally decide how wide this should be? I mean, I think that one of the takeaways I think of your paper is kind of also bringing back some of the context specific or setting specific knowledge that you need in order to do these. And I think that's kind of a trend with a lot of the recent DID literature is bringing some of that stuff back in. So is this something that needs that context to be able to do these, or is this something that there is like an optimal bandwidth type formula that we can kind of use for this?
So I don't have an optimal bandwidth formula. I wish, but there's a paper by Damien Clark. He doesn't introduce it's under a very specific assumption, but he recommends some sort of cross validation where you leave out some units, use different set of rings with different widths, and sort of in a mean squared error sense, try to best estimate the spillovers. In the paper, I talk more about this. For example, how far you spread as you spread further and further away. I'll show you sort of in this Tennessee Valley example. If I were to just keep going and I say, okay, 150 to 250, 250 to 350, eventually I'm just going to run out of units A. So that would be a problem. You wouldn't have any units to estimate your counterfactual trend. And even in this example, you'd have these units, but you'd have very few units, and so you'd have less precise estimates. So there's a variance trade-off. So like if you keep adding more and more rings and you go eventually, your counterfactual trend estimate's going to get more and more noisy. But if you only were to, for example, include this blue ring right here, well, then you might have bias remaining because as my estimate suggests, spillover effects spread all the way up to 200 miles. And so you, by not including all the affected units, you're leaving some bias in. So there's some sort of bias variance trade-off. And so it depends on your context. But for example, like this, I used really large maximum distance because the Tennessee Valley Authority was a massive investment. But if you're looking at like libraries opening, maybe like your context will tell you how far it goes, for example, by driving distance, right? There's a paper by Peter Nenks that looks at like libraries opening up, maybe it's not Peter Nenks. There's one that looks at libraries opening up in the 20s. Well, you can't travel very far in the 20s, 20 miles is quite a big distance to go. So maybe that would be your context can oftentimes guide better than statistical theory, right?
Right. Yeah. Like the local nature of certain types of pollution could influence how wide you have these and these kind of things. Okay.
Yeah.
Awesome. Thanks, Kyle.
Yeah. Other questions? Cool.
Okay. Well, if there are no other questions, I just want to thank Kyle for the great presentation. And I will upload this, and then hopefully, I think Kyle, I'll talk to you about grabbing some code.
Yeah.
I think there's some on your GitHub, but we can see about working with that and uploading some. So thanks again, Kyle, and have a good weekend, everybody.